So a few more, attempts at this, and I did get something that I should have probably figured out earlier, or a way of just counting it earlier, and that is using this. If you have for the kind of like the previous work, for every position within the matrix where you're counting the consecutive above and to left of the elements. So again, that would be if I were to compare a given matrix to what consecutive above and consecutive left means. So for every cell here, consecutive above would give for that position the number of ones, including itself, kind of consecutively from that and above it, and consecutive left would be ones from that position um, to the left. So here this would be consecutive above 3, consecutive above 3, consecutive above 1, consecutive above here. Here is obviously 0. Anytime you have a 0, then consecutively there's going to be 0 ones above it. And here is 1, 2, 2, 0, 0, 1, 1, 0. Consecutive left, this would be 3, 2, 1, 0, 0 obviously. 3, 2, 1, 0, 0, 2, 1, 0. So the matrix for consecutive above, it's going to be ignoring kind of the dummy kind of leftmost column or rightmost column here. Consecutive above this one is like 1, 0, 1. Consecutive above here is 2, 1. Actually, was I looking for the right? This is an example 2. Example 2. Consecutive above was 0, 1, 1, 0. And then this would be 2, 2, 1. This is 1, 3, 3, 0. So 1, 3, 3, 0. Alright, anyways, so given those two matrices, if you were to then try to count the number of submatrices of ones where at any position you consider that position to be the bottom rightmost, then for instance, if I know that there's 3 consecutive ones from here and above it, then there should be 3 possible submatrices that have basically this and a one column submatrix. So it'd be like this one, this 2 by 2, or sorry, this 2 by 1, and this 3 by 1. So the height of the consecutive above is equal to the number of submatrices where that's kind of the base is just 1, base is 1 or the width is 1. And then you extend out here, as long as you can have consecutive ones to the left, that means you can extend out the base of that submatrix or the width of that submatrix to leftwards. And as you extend out, the height of the new kind of column within that submatrix helps to determine how high a submatrix with that extended base can go. So here, because this is 3 and this is 3, then I can extend out full. There's going to be 3 new submatrices where the base is now 2, the height is 1, the height is 2, and the height is 3. But if this was, let's say this was a 0, then because this height was 3 and this height was 2, then it can only go up to the minimum of the 2 heights. So anytime you extend out the base leftwards like this, you can only go as high as the minimum of the new height and the previous kind of height of all the height up to then. So iterating through do I need to actually iterate through, like, okay, well, anyways, I thought iterating through kind of in reverse order. So starting with the bottom left or bottom rightmost corner. Although I don't think it matters actually. Anyways, if that spot is a 0, obviously it can't form any submatrices as the bottom right corner. But if it doesn't, then the height of the initial thing from that spot is going to give you the number of submatrices that is like a one column submatrix from that bottom right position. So here it'd be a 3. And so increments by that. And then going out, going to the left, where k is kind of the number of offset leftwards, or the number of extensions to the base. The height is going to now be the minimum of how many consecutive above from that position is. So here it would be another 3. Extend out here, it would be another 1. The minimum of that, which is going to be consecutive above that new position and the previous height, and then answer increments by that. And that pretty much calculates everything without having to rely on anything else. And the solution ends up being not particularly fast because, oops, I forgot to turn this off. The solution ends up being not particularly fast because there is a fair amount of redundant calculations here. I just need to optimize it. Okay, so it's like 57%. But the optimization here I'm thinking of is if you have a certain position, the sum of the stuff that you're adding from that position, like you're adding 3, 3, and 1 from this position. From this position, you're adding very similarly 3 and 1. So there's some redundant summation here that I can probably do one pass to figure it out what that summation might be, and then not have to iterate over everything. So from this position, it'd be adding 3, adding 3, adding 1. So if I calculate going rightwards here, that the highest thing is going to be 1, and calculate here, the highest thing is going to be 3, but I also take into account the 1. So I can say this is 3 plus 1, so it's 4. And then here's another 3, so this is 10. So here I can immediately know that there's 10. So, okay, so I think maybe I can do something like for every row and range rows, and for every column and range calls. I think I'm going to go ahead and there's kind of I need to, what do I call this? I'll call this some matrix from the, I'll call this the horizontal submatrix because I'm going to need one for the vertical submatrix. Actually, this should probably call the vertical submatrix. This is going to be, I guess it's just going to be 0 times the number of columns for everything in the range of rows. I'll probably need one for the horizontal submatrix times columns for everything in the range of rows. Okay. So at any given position, I'm going to sum of, so this should be 1, and then this should be 3, and this or 1 plus 3 is 1 plus 3 is 4 plus 3 is 10. 1 plus 3 is 4 plus 3 is 7. And this is resets to 0, so it needs to keep track of streaks, I think. Okay, so I think I need to do like a streak of verticals. Streak is 0. Horizontal streak is 0 as well. Okay. Maybe I need to do separate for loops for this. Anyways, so if I go through and do the verticals, so here, if the value is 0, then you need to restart the streak to 0 and just ignore it. So if the matrix at this row and column equals 0, then the vertical streak, oh, this is not how to do it. I wonder if you can do this. I think you can, yeah. Equals horizontal streak, which is also equals 0. And then continue. Otherwise, what's going to happen? Then the vertical streak should should increase by the number of ones above at this point. Vertical streak plus equals consecutive above. So like this thing would be 1, and then this thing 3 above would be 4. And this thing plus 3 is going to be 7. This thing resets to 0. And then the horizontal streak. Well, see, I'm iterating through this way. I think I might need to iterate through this way. Actually, yeah, I think I need a separate for loop to iterate through for every column and then everything in that row. So I'll call this the vertical streak. And then for everything in range, the number of columns for every row and range of rows. Yeah, the order of iteration through, order of traversal through the elements here. The way that I traverse needs to matter. Okay. If this thing is 0, then skip it. Actually, I guess this thing can probably just, since this is one thing right now. Else, that, this is going to be a horizontal streak. I don't know if this is actually any faster. Yeah, this has to be faster, right? I don't need to go through this full loop. Okay. Horizontal streak plus equals consecutive. Consecutive left. 1. So I'm going through every column. Going through every column. And then every row in that column. So going through this column, through the rows in this column. Consecutive streaks. It's not quite right. I think I need to go to consecutive. left 0, 0. So this is consecutive left is going to be 1 plus. Do I even need the? Actually, I don't know if I need the horizontal streak now that I think about it. Just need the vertical streak because I'm going to be adding from every position. Yeah, just need the vertical streak maybe. I'll just comment this out. So if I have that, then for every position, instead of doing this inner for loop of heights, I can add the number of vertical streaks up to this point. So yeah, I think it's just my answer plus equals vertical streak. No, it's going to equal the vertical streak is actually what I put into the vertical sum matrix. That position. In that case, am I just not summing everything inside the vertical sum matrix? Alright, well, this is the right answer, which it isn't. Okay. It's too big by a lot. This. Okay, so let's go ahead and see what the hell the vertical sum matrix has. It doesn't look like it's resetting to 0 correctly. Every time it does a new row, it's to reset the vertical streak to 0. Okay, so that's closer. Very, very close. Okay, so vertical streak here is 1, and this is going to be 2. Like 1 plus 1. Oh, I need to take the minimum at some point. The vertical streak needs to increase by the minimum rather than just consecutive above. Let's see. Yeah, this should be the minimum. So actually, this. So there's a current height, and then there's a current sum. Yeah, I see. So I think this is. Let's say the current height is 0, and this resets every time you see a 0. And the vertical and the sum of the stuff yeah, actually, so the height is 0. Otherwise, the height is going to be equal to the minimum of the current height and the current consecutive above for this position. And I don't think I need the variable. I think the vertical sum matrix at this position is equal to the one to the left of it. Vertical sum matrix row column minus 1 plus the current height. So it extends left. Right? So the vertical 3 tiers 1. This is the height of, let's say, 2. So this is going to be 1. This is going to be 2. And then let's say this is actually 3 height, and this is 2 height, and there's a 0 here. Then when I sum the matrix, this would add 2. This would add 2, then 2, then 1. But from here, it would add 3 and 1. Okay, the summation is actually not fully redundant. So let's add 2, 2, 1. Here, this would add 3. So how would I calculate that quickly? This adds 3. If this was 1, this would add 3, 3. If I go leftwards, should we go leftwards or rightwards? So I know I get 1 here. I know I get 3. Extend this thing out here. The number of things here. It's only 1, but it's fine. Let's say it's 4 here, and there's 3 here. Then I should be able to get 3. I should get 3 here. Like a stack issue here. That's the minimum. It should be the minimum up to this point. So if I go rightwards here and there's 1, then I go rightwards here and it's now 3. So I go 3, I can have 3 in this column, but since this is capped at 1, then I can only go 1 here. It's 1, 3. 1, 3. And here there's another 3 column. So if I add it to the stack, so there's a height stack. 1, 3, 3. if the height stack shrinks, then that thing can be extended to the length of it to the left. The height stack doesn't shrink. Then that so if I have a new item here and say it's 4, 1, 3, 4, if there's a 1 here, then I should be able to do 4, 1, 4 in this column, 3 in this column still, and 1 in this column. 2, 2, 2, 2, 2. Interesting. Say there's another one that's like a 1 here. There's 2 consecutive ones. What happens to the stack at that point? So the 2 here removes the 4 and the 3 because it limits the next heights. So the 2 would become 2, 3. Interesting. Huh. It's like a monotonic stack of heights. Monotonic stack of heights. So there's a 1 and there's a 3. Monotonic stack of heights. Interesting. So you have monotonic stack of heights. So you have a 2, and then if you have another new element here 2, then you maybe replace this 2 with the 2, 2, like 2 height, 2 base. And if you have something bigger, let's say there's 3 here, then that'd be 2, 2, and a 3, 1, 3, 3 height with 1. And I guess you keep track of, what would you keep track of? The sum of the 2, 2, and 3. 2, 2, 2, 3, 2, 2. Oh, interesting. This is going to be a totally different way than, so I don't think I need the summation, the consecutive stuff. Okay. Alright, this is using monotonic stacks. Monotonic stack of heights for every position. Every position, track the heights of possible submatrices up to that position. Okay. So for every row and range rows, column and range columns, I think I need to reset the stack here. stack is going to be empty. Okay. Maybe the stack starts with infinite t just to be because it's gonna go smaller. A smaller thing limits the stuff in the stack or removes tuples from the stack. The tuples have height and width of things. So if I go here, the height is 1, width is 1. So let's say if the position here, okay, actually I can say the value is the submatrix X row and column, and while the stack maybe I can do this. Height is infinity, width. No, it should probably be 0, 0. So when do I pop stuff off the stack? When the height is pop stuff off the stack if the height that I'm dealing with is bigger than the current height. And since I don't want to pop off this last one so that I don't have an empty stack at all, yeah, it needs to be the smallest possible. Yeah, while the top of the stack, the height of it, which is the 0 index, is bigger than the value. I guess it could be bigger than or equal to the value. And then I need to keep track of the sum, the new width. The new width is going to be incremented by, it's going to always be 1. There's always going to be 1. The new width is going to be based on the, maybe I do need the consecutive above at least. I don't know if I need the consecutive to the left, but I think I need the consecutive above. Consecutive above. Actually, I just might as well get both. So the new width is going to be for every row and column. So this should be 1, and this should be 3, 1. Should be 1, 1, 3, 1. Yeah, the new width starts with so if it's a 0, 0, actually I can probably say something like for every column in range, if the value is 0, then reset the stack. Value equals 0. Stack goes back to 0, 0. And then continue. Because if it goes 0 here, then there's no heights to chain onto that. And then if the width, okay, so assuming that's not the case, so that means that there is a 1 here, or 1 here, or 1 here. The stack could be 0, 0. It looks like a 1 here, it could be not 0, 0. Okay. The new width starts with 1 because it's the value here. And the height starts with, to do the height of the stack is currently consecutive above. So it's above the current height, which is consecutive above this position. Consecutive above this position, and I'm going to, while this value, so 1, 3, while this value is smaller, while the height is smaller than or equal to, then it's going to limit this. And the new width is incremented by whatever the width that would be here. Stack of -1, entry 1, and then pop that in the stack. Okay. You need to keep track of the current stack sum as well, I think. Current stack sum. Keep track of the current stack sum. I guess just another variable. Current stack sum is the sum of the heights and widths. Yeah, okay, so stack sum is equal to 0 here. And when I pop an element off the stack, stack sum needs to be removing the number of possibilities that that element had. So I think that would be height times width of that element. Stack height and width of that. And then I pop it off the stack. So I pop, pop, pop. So if this was, let's say, so I had a 1 here, 3 height here, and then a 2 height here. Then I need to pop off this. Well, let's say it was actually, let's say it's 1, 3, 3, and 2 here. Let me pop this off. Well, technically this is one thing. It's going to be 3 height, 2 width. So I pop this off and I remove one possibilities here, and that'd be 6. Okay. And then keep on popping it off. Keep on incrementing the width of the new element that will be added eventually here, and then eventually I'm going to add stack, append the new number of rows, or the new height, which is going to be consecutive above. Actually, right. yeah, consecutive above the position, row, column, and whatever the new width is, based on all that popping. Stack sum increases by whatever I just added. The number combinations that are consecutive above at this row, column, times the new width. And then I increased my answer by the stack sum. Okay, line 53. Okay, I just need to comment this out. Submatrix not defined. Oh, this I think was matrix. Answer not defined. I guess I could just compare this to be this matrix of this row and column. Well, that was a journey. I don't need the consecutive left. I do need the consecutive above. Do I need the consecutive? Yeah, I need the consecutive above. I'll just use value here. Actually, I could probably just use if value equals 1, then do this. If material at this row and column equals 1, consecutive above increases by that. Actually, can this be one pass actually? Like, I don't think I need to do 2 passes because this thing, the calculation of this thing is simultaneously not calculation of this thing is simultaneously can be done with this thing. Okay, I can do 1 pass, huh? So but maybe this looks better if I decompose it like this. Do a lot of things simultaneously. Yeah, 2 passes is fine. I wonder if I should just do the next daily. 88%. Sounds pretty good. Stack sum for every column. If the value is 0, reset the stack. And reset the stack sum. I wonder if I should reset. Maybe this is not necessary. Value 0, reset the stack and everything. So that's probably faster than trying to remove all the elements that would be there manually. Yeah. Otherwise, the width of the new height the new rectangle will be 1 by default. Pop off the stuff from the stack that has heights that are bigger than this one, because this one might be limiting it. And then the new width is whatever width was previously there, now going to be chained onto this height. And the stack sum removes that combination. Pop, includes append, stack sum increases, answer increases. Alright, this is as optimized as I think I'm going to try to get. Alright, pretty good, pretty good. So summary, it ends up being, this is my old solution. Yeah, okay, so summary is something kind of monotonic. So a monotonic stack is going to be a stack where all the values in it are maintained to be always increasing or decreasing. In this case, it's going to be increase instead of heights. So maintain to help with calculations. Pre-calculate to help with to make easier actually to decompose solution. Pre-calculate the number of consecutive ones vertically above from any position. So that's a 2D matrix of values there. So that's this thing right there, consecutive above. And then iterate over every position. Oh my god. Maintaining a monotonically increasing stack of tuples, height, width, that represents the possible left side adjacent submatrices for that position. So let's say I'm iterating over the positions in this last row. Monotonic stack will always start with 0, 0, so there's like 0 height, 0 width to the left of this. And then it's going to be 1, 1, so this is representing that this is height 1, width 1 at this point. And then here it's going to add a tuple that is height 3, width 1. And then here, it could in theory add another tuple that's height 3, width 1, but we'll pop this tuple off 3, 1, and then it'll pop on a tuple that is 3, 2. This is going to represent 3 height, 2 width. And then let's say there's a 1 here. So this 1 with this height of 2 means that like the number of submatrices here onwards are going to be the 3 here are too high. Like the combinations here. This is going to remove this tuple of 3, 2 because the height is too high. And it's going to put onto the stack a tuple of 2, 3. The lower height where the width is now 1 more than the width that is removed here. And what that kind of represents is the stack represents the number of rectangles that can be formed from this position, where in this position you can form a 2 by 3 and then a 1 by 1, or 1 by 1, which is like a 1 height, 1 width additionally. Yeah, additionally to whatever was previously added. Iterate over possible, maintain monotonic increase in tuples. Whenever a value is 0 at that position, reset the stack. This is going to be to 0, 0, and sum stack variable to 0. The sum stack variable calculates the number of implied submatrices of the current stack of possible heights and widths. Sum stack variable tracks the possible submatrices of heights times widths on the stack, which is the sum of those values, of those products. Whenever a new height that is bigger, or whenever a new position has a height that is bigger, that is actually smaller than the top of the stack, pop, decrementing the sum stack as decrementing the sum stack variable appropriately, tracking the new width, or incrementing the new width by the width that was popped. And then afterwards, actually this is while, whenever and while afterwards add onto the stack the new height width combination and increment the sum stack variable, increment the answer by the sum stack variable. Sum stack variable keeps track of basically the number of combinations of submatrices that would be possible with this new row column position. So yeah, very similar to other monotonic stack kind of deal, where you have some for loop that, or some while loop that will maintain the monotonic property. In this case, it has to be an increasing monotonic stack. So if the new element that would be added would break it, then you pop off the stack values that are kind of, in this case, smaller or bigger than it, so that it maintains the monotonic increasing property, and post that while loop or for loop, you add onto the stack the new element, and then do whatever you do with the calculations of the answer based on it. Alright, time complexity, this can be O of n by n to iterate over every position in the matrix necessary to do the monotonic calculations and the consecutive above calculations. Space complexity, this is going to be O of mn as well. To have, actually, yeah, I need to keep track of the consecutive above to have the pre-calculated consecutive above values. Technically, the consecutive above, wonder if the consecutive above could possibly be a single matrix, single ray. Yeah, technically could make the consecutive above matrix into an array instead, and makes it O of n, where n is the number of columns, or or rows if you try to optimize in that fashion.